The title of the paper is Attention is All You Need. The main three authors are Ashish Vaswani, Noam Shazir, and Nikki Parmar, and the work was done at Google Brain and Google Research. The paper was published in 2017 at the Neural Information Processing Systems Conference, often called NeurIPS. This paper asks a very specific question. Do we actually need recurrence or convolution to model sequences like language, or can attention alone do the job? Before this work, the dominant models for machine translation and language modeling were recurrent neural networks, especially LSTMs, sometimes enhanced with attention. These models process text one token at a time. That sequential structure created two major problems. First, training was slow because each step depended on the previous one, which limited parallelization on modern hardware. Second, learning long-range dependencies was difficult because information had to pass through many sequential steps. The transformer, proposed in this paper, removes recurrence and convolution entirely. Instead, it relies only on attention mechanisms to relate tokens in a sequence. The key shift is that the model looks at all tokens at once and learns how strongly each token should attend to every other token. This allows global context to be modeled directly and in parallel. Architecturally, the transformer still follows an encoder-decoder structure, which made it easy to compare against existing translation systems. The encoder reads the input sentence and produces contextual representations. The decoder generates the output sentence one token at a time, attending both to previously generated tokens and to the encoder output. What changes is how these components are built. Each encoder layer consists of two parts: multi-head self-attention, followed by a position-wise feed-forward network. Each decoder layer adds a third part, which is encoder-decoder attention. Residual connections and layer normalization wrap every sublayer, making deep stacks trainable. At the core of the paper is scaled dot product attention. For every token, the model computes three vectors: a query, a key, and a value. The query represents what the token is looking for, the keys represent what other tokens offer, and the values contain the information to be combined. Attention weights are computed by taking dot products between queries and keys, scaling by the square root of the key dimension to stabilize gradients, applying a softmax, and then forming a weighted sum of the values. This process lets each token selectively pull in information from all other tokens. Multi-head attention extends this idea by running several attention operations in parallel on different learned projections of the same input. Each head can specialize in different types of relationships, such as syntactic structure, semantic similarity, or long-distance dependencies. The outputs of all heads are concatenated and projected back into the model's main representation space. This design increases expressiveness without a prohibitive computational cost. Because attention alone has no built-in notion of order, the paper introduces positional encodings. These are vectors added to token embeddings that encode position using sine and cosine functions at different frequencies. This gives the model access to both absolute and relative position information while remaining fully parallelizable. From an engineering perspective, the transformer has major advantages. Self-attention allows all tokens in a sequence to be processed simultaneously using matrix operations that GPUs and TPUs handle efficiently. The path length between any two tokens is short, making it easier to learn long-distance dependencies. The main drawback is that attention scales quadratically with sequence length, but for typical translation tasks, this was a favorable trade-off. Experimentally, the paper showed that transformers achieved state-of-the-art results on major machine translation benchmarks, while training significantly faster than previous systems. The authors also introduced training practices that became standard, such as learning rate warm-up schedules and label smoothing. The broader impact of this paper is hard to overstate. It established attention as the central building block of modern AI models. Transformer variants now dominate natural language processing, powering models like BERT, GPT, and T5. The architecture has also spread beyond language into vision, audio, and multimodal systems. Most importantly, the transformer scales exceptionally well with data and compute, which directly enabled the rapid progress of large language models. In essence, attention is all you need did not just propose a better model, it changed how researchers think about sequence modeling, replacing time-stepped computation with global, parallel attention. And in doing so, it laid the foundation for today's AI systems.